In this video, we are going to learn about obstacle detection algorithms. Here is the example that we are going to use to learn how to design obstacle detection algorithms. We have our robot in this map. It needs to keep going forward until it is 10 centimeters or 0.1 meter away from this basket here. For example, we may place the robot at this safe distance from the basket and lower the object in its arm. So the basket is our example obstacle. The robot is equipped with an ultrasonic sensor that will tell us how far the obstacle is away from the robot. Obstacle detection is a basic way to perform localization for robots. Localization is the ability of a robot to know where it is on the map. Please look at the links in the resources section to get more information about additional localization algorithms using sensors such as ultrasonic sensors, radars, cameras, etc. In this video, we will focus only on ultrasonic sensors. So, to help us design the obstacle detection algorithms, we will first understand the fundamentals of the sensors involved in obstacle detection, namely the ultrasonic sensor. We have been talking about the use of simulation to design algorithms throughout this training. We will next look at how to create maps from pictures to help with designing obstacle detection algorithms. This will be like the line following maps we generated in the previous video. Then we will look at two different algorithms to perform obstacle detection. The first one is called the on-off algorithm, and the second one is through a PID controller, which we have talked about in a previous video. Let's first look at the sensors to understand them. Here is an example obstacle, and here is the robot trying to detect it. The ultrasonic sensor is fixed in front of the robot. This emits ultrasonic waves and measures the waves reflected from the obstacle surface to give a value corresponding to the distance of the obstacle. So the farther the robot from the obstacle, the higher the value returned by the sensor. Ultrasonic sensors usually have three important values that characterize them. The first one is called the maximum range. This tells what is the farthest distance that the sensor can measure. The second value is called the minimum range, and this tells what is the minimum distance that the sensor can measure. The last value is called the resolution, and this tells us what is the smallest change that the actual ultrasonic sensor can detect. We can note down all these values from data sheets or by using experiments. Let's take a look at a video of an actual robot to understand these sensors. Here is a sensor in front of the robot. We are looking at the value returned by the sensor. This is the closest obstacle that it can see. In this case, the basket. The sensor value starts around 0.8 meters, and as the robot is manually moved slowly, the value keeps decreasing. This is because the robot is approaching the obstacle. We can also see some zero values intermittently. Sometimes sensors could drop values, and this scenario needs to be considered when building the algorithm. Towards the end, the sensor shows 0.02, even when the sensor is literally touching the obstacle. This is the characteristic of the sensor, since it can only measure 0.02 meters as a minimum distance. This is also called the minimum range of the sensor. Let's note these values from the datasheet here. So the maximum range is 2 meters, the minimum range is 0.02 meters, and the resolution is 0.01 meters. These values were noted from the datasheet for the VEX platform. Now that we have understood the characteristics of the real sensor, let's see how to bring this information into our simulation. In the real world, the robot travels over the map, and the ultrasonic sensor provides us with a value corresponding to objects in front of it. For the simulation, we will take a picture of the full map and manually denote the position of these obstacles in the map. To do this, we will use the app that is provided as part of the training, called the Simulation Map Generator. Recall that we use this app to generate maps for line following as well. This will give us the ability to mark obstacles on actual fields and test algorithms on our own maps. Let's switch to MATLAB to see how to do this. In the current folder, we see a picture called vexmap.jpg. Let's open this outside MATLAB to see that it is the path that we are trying to navigate. This can be any image of a path that you might be interested in bringing into the simulation. Our objective will be to place obstacles in the region of interest. In our case, we have only one obstacle, which is the basket. So let's use a simulation map generator. Let's go back into MATLAB, and under the Apps tab, let's choose the simulation map generator. The first step is to load the picture, which can be used as a reference to place the obstacles. So let's click on the Load Map Image button. And let's select the vexmap.jpg image. This pulls up a preview of the image on the right-hand side of the interface. Next, we need to specify the size of the map in meters, where x is along the horizontal axis and y is along the vertical axis. Using a tape measure, we determine this for our map to be 3 and 1.5 meters. So let's insert it right here. Hitting enter enables the next option. Now we need to specify what type of map we're trying to generate. Since we are only concerned with obstacle detection in this video, let's choose the obstacle option. We talked about line following maps in the previous video. If the robot's trying to perform both line following and obstacle detection, then the both option might be useful. We will see how to do this in the next video. So let's choose the obstacle option for now. As soon as you select the obstacle option, the preview changes to a blank white image. This means that currently there are no obstacles on the map. The idea is to place obstacles on this map so that obstacles look black and everything else looks white. So first we need to specify how many obstacles we would like to place on the map. The default option is 2. We can change this to 1 since we only have one obstacle in our map, just like I'm doing over here. After setting this value, hit the Place Obstacles button. This opens a new window with the original map picture. To place the obstacles, click and draw a rectangle in the image over the region of interest, just like I'm doing right here. Once the region of interest has been selected, double-click inside the region, and now we can see that the obstacle has been placed in the map preview. We will use this map for our obstacle detection simulation. If we have more than one obstacle, we can simply change the number of obstacles appropriately and repeat the obstacle placement process for each of the obstacles. Once the preview looks acceptable, let's hit the Export Map button. And let's give it a valid name. So let's call it Obstacle Map. And let's hit Save. Once the file is saved, we see a success message. We can now load the file that we've just exported and use it for simulation. To do this, let's go back to MATLAB and double-click on the obstacle map.mat file that has been created in the current folder. So let's double-click this. And this creates a variable called map4sim in the MATLAB workspace. We can use this variable for our simulations. To set up our obstacle detection simulation, let's open a new Simulink model. Let's go into the Simulink library browser. And from the mobile robotics training library, let's add the ultrasonic sensor to the model. This block will represent our real ultrasonic sensor. Let's double click on the block to set up its parameters. We see that the map variable has already been set as map4sim. This is the variable we just loaded in MATLAB. Apart from this, we can also specify sensor characteristics. For example, we use data sheets to find values for the range and resolution of our sensor. We can specify these values here to make the block output values like the actual sensor we are trying to model. We can also specify a sensor offset here that specifies where the sensor is positioned with respect to the center of the robot. Let's leave it as 0, 0 for now. Let's hit OK. Now going back to the mobile robotics training library, let's add the robot simulator block into the model. And let's double click on it to set up its parameters. For the obstacle detection simulation, like in the line following simulation earlier, we need to set the map variable to map4sim. So let's go ahead and do that. And recall that map4sim is a variable that we just created in the MATLAB workspace. Once we specify the variable, let's hit apply. This brings up another window with the updated map. Note that the robot starting position is 1, 1 here. If we wanted to specify it to be anywhere else interactively, let's go back to the parameter dialog and choose the Set Position Interactively option. This brings up another window of the map. You can double click on the point that we want to set the position to. So let's double click here. And now we see that the position has been updated in the parameter dialog. Now let's hit the apply button again. And now we can see that the robot has been put at the starting position that we just selected. However, the robot is facing towards the right. We need to position it such that it is pointing in the upwards direction. So let's set the initial theta value to 90 in the parameter dialog. And now let's hit apply again. Now our robot is facing the obstacle and we can implement our obstacle detection algorithm to see if we can find the obstacle at an appropriate distance. Let's go back to the presentation and do a short recap. To set up an obstacle detection simulation, we began with the simulation map generator. We loaded an image of the map and then specified the track size. For the obstacle detection map, we then talked about placing obstacles interactively so that the obstacles look like black rectangles on the map and everything else is white. Finally, we exported the map to a mat file. We then loaded the mat file and saw the map for sim variable to be used for simulation. We have specified this variable in the ultrasonic and the robot simulator blocks. Here are some of the best practices to use the simulation map generator for obstacle detection simulation. Make sure the track size measurement is accurate enough. This directly affects how the distance measurements are made in the map. Also, approximate obstacles as rectangular blobs. Now that we have set up the simulation, let's implement an obstacle detection algorithm and see it in action. One of the more popular obstacle detection algorithms is called the on-off algorithm. The basic logic for this is as follows. We first check the value returned by the ultrasonic sensor. If it is greater than a threshold, then the robot is still a distance away from the obstacle. We must keep going forward towards the obstacle. If the sensor value is less than the threshold, that is, the robot is within the threshold distance from the obstacle, we must stop. Let's put this logic in a flowchart format to better understand the algorithm. We first check if the sensor value is within the threshold value. If not, we keep moving forward. Else, we stop. Since the algorithm has only two states that it can move between, it is called an on-off algorithm. Let's switch to MATLAB to see how we can do this. Let's open the starter model object detection _ start. The model already has several blocks to start with. Notice the ultrasonic sensor and the simulator block that we set up earlier in the video. It also has blocks that we have already talked about in previous videos, namely the motor and the lookup table blocks. Our goal is to now use the ultrasonic sensor information to generate the linear velocity v value to help the robot stop 0.1 meters away from the obstacle. So let's use stateflow for this. Let's start off by saving the model as obstacle detection _ on-off. And let's hit save. From the Simulink library browser, let's add a stateflow chart to the model. And now let's double click on the stateflow chart to define the logic. Just as we discussed in our flowchart before, there are two states in an on-off algorithm. So to add a state, click the state option on the toolbar on the left and drag it into the model. You can copy a state in the same way that you copy Simulink blocks by right-clicking and dragging. So now we have two states. Let's call the first state the go forward state, and the second state the stop state. Our robot will go forward by specifying a constant velocity value. For example, v equals 0.2. And for the stop state, we will set the same v value to 0. So let's define the logic. In the go forward state, we set v equals 0.2. And in the stop state, we set v equals 0. Since our algorithm can shuttle between these two states, let's connect them with the back and forth connection. just like we did in the previous videos. Next, we need to define the condition that will decide moving between these two states. So we know that when the ultrasonic value is less than or equal to the threshold, it will move from the go forward to the stop state. So let's define that. And when the ultrasonic value is greater than the threshold, it will move from the stop state to the go state. So let's define that as well. So let's resolve the symbols in this chart. Recall that to resolve the symbols, you go to the View tab and choose the Symbols option, which pulls up the pane on the right-hand side of the screen. You can resolve the symbols by clicking on this exclamation mark up here. And now we can see that threshold and ultrasonic values have been set as inputs and V has been set as an output. The next thing to do would be to go up one level in the model and connect the ultrasonic block to the input of the chart. So as you can see, we've got two inputs and one output to the chart. And the ultrasonic sensor will connect to the ultrasonic value input. And the V value will connect to the utility block. Now, the threshold is the reference distance from the obstacle. So let's connect the threshold constant block to the input of the chart. And notice that since we are only moving in a straight line, the omega value has been set to 0 using the 0 omega constant block. Let's also connect the output of the ultrasonic sensor block to the obstacle distance scope over here. This will help us visualize the ultrasonic sensor data. Let's go back into the state flow chart and let's run our model. We see that the robot moves in a straight line and stops just before the obstacle. In the chart, we can also see that the states shuttling from the go forward to the stop state. Let's go back up to the top level of the model and view the obstacle distance scope. We can see that the robot moves towards the obstacle and stops when the obstacle is a little less than 0.1 meters away. Note that the distance value goes below 0.1. This is because we are asking the robot to stop immediately from a velocity of 0.2 to 0, which is not physically possible. This results in the robot going beyond the threshold value, and we can see a staircase-like response. This is because of the way in which we model the sensor using a resolution parameter, which is the minimum distance that it can see. Now we use this simulation to test the obstacle detection algorithm. Let's look at how the actual robot performs with this algorithm. Let's go back to the presentation. We just saw how to implement the on-off obstacle detection algorithm. We see that the robot went beyond the line that signifies the 0.1 meter distance to the obstacle. Our simulation showed a similar result. The advantage of this algorithm is that it is simple to implement. The result could be inaccurate based on how fast the robot is traveling. We can achieve smoother and a more accurate stop for obstacle detection using PID control. Let's see how to do this next. Here we have our robot that is actuated by the motors. Using an ultrasonic sensor, we can monitor the current distance to the obstacle. We can then compare this with a desired reference value. This is the threshold value that we talked about during the on-off discussion. Using these two values, we can calculate an error. This error can be fed into a PID controller. Note that the PID controller outputs a velocity V value based on the input error. The omega value is still 0 since the robot is moving forward in a straight line. Let's switch to MATLAB to see how to implement this. Let's open the starter model obstacle detection _start, just like we did earlier. Our goal is to use the ultrasonic sensor information to generate the V value to help the robot stop 0.1 meters away from the obstacle. We will use a PID for this. Let's save this model as obstacle detection _PID. Now first we need to compute the error between a desired value and the actual value. So let's add a subtract block to our model from the math operations library in the Simulink library browser. Now, our desired value is the threshold. So let's connect that to the positive sign of the subtract block. And the actual value is the value given from the ultrasonic sensor. So let's connect that to the negative port on the subtract block. Let's also connect the output of the ultrasonic sensor to the obstacle detection scope. This will help us visualize the value. Now next, let's add a PID controller from the mobile robotics training library. And let's connect the PID controller to the subtract block. The PID will output the V value for the robot. So let's connect it to the V signal right here. Since our robot is moving in a straight line, the omega value would be 0. And that is given from the 0 omega constant block. So now let's double click on the PID controller to set up its parameters. Let's choose the P only controller first. And let's set its gain to the default, which is 1. Now let's go into the PID advanced tab and set the output limits of the controller. So let's limit the output. And recall that our controller output is the linear velocity of the robot. And that is constrained by how fast your motors can rotate. We already calculated this value in the using PID controllers video to be 0.67. So let's set the upper saturation limit to be 0.67 and the lower saturation limit to be negative 0.67. Let's hit OK. And now let's run our model. We see that the robot is moving in the backwards direction instead of forwards. The reason for this is the output of the controller, which is the linear velocity V, is negative. This happens because the ultrasonic sensor value decreases as it gets closer to the obstacle. So we need to flip the sign of the gain to get the correct behavior of a positive linear velocity. So let's go back into the PID controller block and let's set its proportional gain to be negative 1. And now let's run the model again. We now see that the robot is moving forward and stops at a particular distance from the obstacle. Let's go to the obstacle detection scope to visualize the results. Now here we can see that the robot stops exactly 0.1 meters away from the obstacle. Recall from video 2 when we discussed the basics of the PID that a P-only controller might result in an offset or a steady state error. So it is a good idea to include an integral term. Let's go back to the PID controller parameter dialog and let's choose the PI controller. Now let's set the I value to something small. Let's say negative 0.02. Let's hit the OK button. And now let's run the model. You can see that the robot approaches the obstacle, but starts slightly oscillating towards the end. Let's go back to the distance scope to see this behavior. This is also called chatter. In simulation, it looks like a square because of the way in which we model the sensor using the resolution parameter. In real life, it usually gets damped by the robot mass and the wheel friction and other reasons. In any case, let's reduce the I gain to something much smaller. So let's go back to the PID parameter dialog and let's set this to negative 0.001. Let's hit OK. And now let's run the model again. We now see that the robot is not oscillating as much. And this can be confirmed from the obstacle distance scope as well. Let's look at the robot performing obstacle detection using the PI controller. Let's go back to the presentation. In the video, we see that the robot starts fast but gets slower as it gets closer to the obstacle. We can see that it ends up closer to the desired distance to the obstacle as compared to the on-off algorithm. We can also see that the robot is not oscillating much towards the end. This is because in the real world, sometimes some of the smaller noises are damped due to either the mass of the robot or initial friction of the motor or some other reason. We just saw how to implement obstacle detection using PID. To summarize, we saw the basics of ultrasonic sensors. We then looked at how to create obstacle detection maps for simulation using the simulation map generator. We then took a look at how to use the ultrasonic sensor and robot simulator blocks to visualize our simulation. Then we learned about the on-off obstacle detection algorithm and implemented it using a state flowchart. And finally, we talked about using PIDs to perform obstacle detection and saw that it gave us a smoother behavior. In both these algorithms, we saw how they performed on the hardware. This concludes the video. Throughout this training, we have talked about 3 different applications until now, namely dead reckoning, line following, and obstacle detection. We also talked about different algorithms to implement each one of them. In the next video, we will talk about bringing these applications together to perform predefined path navigation by scheduling when to run these algorithms.